Hello! Today I'll be introducing chaos in the network. Have you ever wondered why small changes in a complex system can lead to completely unpredictable outcomes? This is because of a phenomenon known as topological chaos, which arises in complex networks. From social networks to transportation system, complex networks are all around us, and understanding how they behave is crucial. In this video, we will explore the concepts of topological chaos and its relationship to complex network. So get ready to dive into the fascinating world of complex network and topological chaos. Before explaining topological chaos and network topology, it is important to give an idea of what is topology. The basic explanation of topology is when the properties of a geometric object that are preserved under continuous deformation such as stretching, twisting, crumpling, bending, that is without closing holes, opening holes, tearing, gluing, or passing through itself, it remains the same. That is the basic explanation of topology. Like this coffee cup becoming a donut, the material inside of it is still the same, but it became a donut. The motivating insight behind topology is that some geometric problems depend not on the exact shape of the object involved, but rather on the way they are put together. In one of the first papers in topology, Leonhard Euler demonstrated that it is impossible to find a route through the town of Koenigsegg that would cross each of its 7 bridges exactly once. I hope I pronounced it right. This result did not depend on the length of the bridges or on their distance from one another, but only on connectivity properties, which bridges connect to which island or river bank. Now that we know what is topology, we can move into network topology. Network topology refers to the arrangement of nodes and edges in a network. The topology of a network can greatly affect its behavior and performance. For example, in a random network, nodes are connected to each other randomly, while in a scale-free network, a few highly connected nodes, known as hubs, are connected to many other nodes. In a small world network, nodes are connected to their neighbors and few randomly chosen distant nodes, creating a balance between local and global connections. Understanding the network topology is important for understanding complex systems, as it can greatly affect their behavior. For example, in a random network, information may spread slowly due to the lack of highly connected nodes, while in a scale-free network, a few hubs can greatly influence the behavior of the entire network. Now that we have known about network topology and topology, we can move into chaos theory. Chaos theory is the study of deterministic systems that exhibit unpredictable and seemingly random behavior. A deterministic system is one where the future behavior of the system is completely determined by its initial condition. However, in the chaotic system, small changes in the initial condition can lead to large changes of the system behavior. Chaos theory applies to many complex systems, including weather patterns, financial markets, and the behavior of heart. In these systems, small changes in initial condition can lead to vastly different outcomes, making prediction and control difficult. In complex network, chaos theory can help us understand how small changes in the network topology can affect the behavior of the system, leading to the phenomena such as topological chaos. Here we have an animation of a double rod pendulum at an intermediate energy showing chaotic behavior. Starting the pendulum from a slightly different initial condition would result in a vastly different trajectory. The double rod pendulum is one of the simplest dynamical system with chaotic solutions. Now we can finally go for topological chaos. Topological chaos is a type of chaos that rises due to the structure of complex networks, and it can be visualized with a chaotic attractor. Here we have an image of a chaotic attractor from a neural network model. The chaotic attractor represents the system's trajectory in phase space, and the complex structure of the attractor reflects the topological feature of the network. In a complex network, small changes in the network topology can lead to large changes in the system behavior, and this can be seen in the shape and the structure of the chaotic attractor. As we make small changes to the network topology, we can observe how the structure of the chaotic attractor changes, reflecting the topological changes in the network. Why is it important to understand topological chaos? Understanding topological chaos in networks especially is important for a number of reasons. Firstly, it can help us better understand and predict the behavior of any complex system, such, for example, social networks, ecological networks, and neural networks. We can design more efficient networks by understanding how small changes in the network's topology can affect its behavior. Secondly, understanding topological chaos can help us develop strategies for controlling and manipulating complex networks. For example, in the field of neuroscience, researchers are using topological principles to develop new treatments for disorders such as epilepsy and schizophrenia, which are characterized by disruptions in the brain's network structure. Finally, understanding topological chaos can help us better understand the fundamental principles underlying complex systems in nature and how they evolve and adapt over time. By studying the behavior of complex systems, we can gain insights into how natural systems such as ecosystem and biological system operate and how they are affected by external factors such as climate change and disease outbreaks. To illustrate this concept, we'll be using simulations in Python. First, let's generate a random network with a given topology using the network X library. We'll create a network with 50 nodes and a probability of edge creation of 0.3 using Edras-Renay model. Next, we will simulate the dynamics of a system on this network. We'll start with a random initial state for our system consisting of 3 variables for each node in the network. We'll then run the simulation for 100 units of time with a time step of 0.1. To update the state of our system at each time step, we will use a nonlinear function of the dot product of the network adjacency matrix and current state of the system. Finally, we'll plot the resulting trajectory of our system in 3-dimensional phase space using matplotlib library. And there you have it, a simulation of topological chaos on a random network topology. What if we run this again? Ah, we have another one that is not exactly the same, but it's the same code. What if we run it again? Oh, we have another one which also looks really different. Now we have 2 more, and all of them looks different but has the same node. This explains topological chaos in a complex network. And now we can talk about the examples here of the networks that exhibit topological chaos. These are all small world networks, ecological networks, social networks, neural networks. These all exhibit topological chaos. So now that we know the networks, but how do those networks exhibit topological chaos? One of the causes are small changes in those topology that lead to large changes in the behavior, because a network's topology determines how information flows through the network, and small changes in network structure can affect how information is processed and transmitted. This can actually lead to unexpected and unpredictable behavior that is difficult to model or predict. Also, emergent properties of complex networks. Complex networks can exhibit emergent properties, which results from the interactions between the nodes and edges. And these emergent properties can be difficult to predict or control. As the complexity of the network increases, so does the likelihood of the emergent properties and topological chaos. Together, these causes can lead to topological chaos in networks, which can have important implications of various fields. By understanding the causes and the nature of topological chaos, researchers can develop new strategies for modeling and predicting the behavior of complex networks and design more robust and resilient networks that can withstand small changes in their topology. Overall, the study of topological chaos in networks is an exciting and rapidly evolving field of research, with important implications of our understanding of complex systems and our ability to design more efficient and resilient networks. In conclusion, topological chaos is a fascinating phenomenon.